Right, so in this video I'm going to have a look at functions, and in particular I'm going to have a look at injective, surjective and bijective functions. So just have a look at what a function is or what a function isn't first of all. If we take our function, let's say we'll call it f, and we have our domain here and our codomain here. So we have inputs along here and we have maybe some outputs here, just represented by these dots. And if we take arrows going from, say, this input to this output, this input to this output, this input here to this output, and so on. This here is our function, okay? It maps these four here to these three here. So this is our domain here, and this is our codomain representing these four dots, but the range is actually only these three dots here. The range is they're the elements that are the actual outputs. The codomain is what represents all the possible outputs. So this is a function here. Now you can see that each input here is mapped onto an output. This input here and this input here happen to be mapped onto the same output, and that's okay. Now if on the other hand we have, let's say we'll take another domain and codomain, we'll call it, let's say, C and D, and we'll call the function G, and we have some inputs here and outputs. Let's say we have an arrow going from here to here, an arrow going from here to here, an arrow going from here to here, and let's say we put one more here. So these three inputs are matched to these four outputs here. But look what's happening here. This particular input is mapped to an output, so that's fine. This particular input here is mapped to two different outputs. That's not possible in a function. So this here is not a function, whereas this here is a function. You have four inputs, but you have two inputs here mapped to one output. That's okay. Here you've got one input mapped to two different outputs. That's not possible in a function. So for example, let's say f of x was equal to x squared here. So anything we put into our function here, we're going to square it. Now this here could be, let's say, it could be a 2, or it could be a minus 2. So our x's, this could be, let's say, 2 here, this could be minus 2, and they would be both mapped to 4. So if you put 2 into x, if you put 2 into our function f, square it, you get 4. If you put minus 2 into our function f, you get 4 as well. So they're both mapped to 4. Now on this function here, g, it's not possible to put a value x into a function and, you know, get two different answers. So it's like if you take the analogy of a, I don't know, a remote control for a television, and you've got buttons here, and let's say this button here is marked number 1, this is here is marked number 2, 3, and so on. If you press this button, you get a particular station. We'll say station ABC. And if you press this button here, you get a different station, let's say channel 4. If you press number 3, you'll get, let's say, channel 5, something like that. Now, if on the other hand you press button 1, it's not possible just to press button 1 and get, let's say, channel ABC and channel 4 at the same time. Two channels can't appear on the television at the same time by just pressing one button. So that's not possible. However, it is possible to have two different buttons programmed in. So say this is button number 7 and 8, for example. It is possible to press button 7 and get channel 5, and press button 8 and also get channel 5. It's possible to program your remote to do that. So if we had this situation, that is possible. So this would be representative, or analogy, if you like, to represent a function. Whereas here, you can't have one button giving you two different stations. So that would be this situation here. Okay, so that's what a function is or isn't. So let's have a look at injective functions. Okay, so we're going to look at injective functions. Okay, so let's have a look at injective functions. These are also called one-to-one functions. One-to-one functions. Now, the definition here is that every output is the image of a unique input. Every output is the image of a unique input. So what does that mean exactly? Well, let's say we take our mapping diagrams again. So we'll take our domain and codomain, and we have, let's say, some elements in our input and some elements in our output here. Now, if we have our mappings, then say this element is mapped onto this element, this one onto this one, this one onto this one, and let's say this one onto this one here. Every output here is the image of a unique input in this particular case. Every output is the image of a unique input. Now, if we were to take, let's say, this function here, and again we have our elements here, and we have some elements in our codomain as well. If you take, for example, an arrow going from this input to this output, this input here to this output, and then let's say we take this input also going to that output here. Now, in this particular case, every output here is not the image of a unique input. This output here is the image of this input and this input here. So therefore, it's not the image of a unique input. It's the image of two inputs. So that's not possible. So graphically, how does that work? Let's say if you draw a graph of let's say a linear function. So it's going to look something like this. It's going to go up here like this, and let's say it goes on forever in this direction and on forever in this direction here. So it's mapping real numbers, if you like, onto real numbers. So let's see. If you take any output here, any output along the y-axis, this is our y-axis, this is our x-axis here, and they both go off in both directions forever. So every output is the image here of one input. So if you take any point on our line here, x, y, it will have this particular output here, this y value here, and there is only one input. There is only one input that will give us this particular output y. So how do you test for that? Well, you can do what's called a horizontal line test. So if you take any kind of horizontal line and move it up and down within your codomain, if it hits the graph only in one place, then it is injective. So if you take any horizontal line, move it up and down, so long as it only hits the green line here, the actual function, in one place, it is injective. So if, for example, you have something like this, and our function, let's say, is a quadratic function, so it looks something like this, for example. If you take any horizontal line, so draw a line across here, bring it up along here, you can see that our horizontal line here will hit the graph here in two places. So it will hit the graph here and here, which means that this particular output, this y value here, so remember that point there has an xy, this one here has, we'll call it an x2y, so we'll call this x1y, x2y. You can see that the y value here is the same in both cases, but there are two different x values. There are two different inputs. So you've got an input here and you've got an input here. This here is our x1, this is x2. So if we put x1 or x2 into our function, we will get y. So in other words, if we put x1 into our function, or we put x2 into our function, we will get one value y. So this output y is the image of two different inputs. So this is our horizontal line test will show that. If you take any horizontal line, move it up and down along, if it hits the graph in two places or more, then it is not injective. Here, each output is the image of only one input, so therefore it is injective. So that's our injective type functions. Okay, so let's look at the next one then. That's called surjective functions. So now we're going to look at surjective functions. Okay, so surjective functions then are also called onto functions. And the basic definition for this is that every element in the codomain is an output. So in other words, we're using every single element in the codomain as an output. By definition then, our codomain is in fact the range. Remember, the codomain contains all the possible outputs, and the range, that's all the actual outputs. But in surjective functions, the codomain and the range will be the same thing, because every element in the codomain is an output. So for example, again, if we draw our little mapping diagrams, so we'll draw a little oval here and here. So we've got our inputs here and we have our outputs here. So if we draw an arrow from here to here, from here to here, here to here, and let's say here to here as well, so you can see that every single element in our codomain is in fact an output. So this is surjective. Okay, so let's draw another one here. So say for example, we've got our domain here and our codomain here. So we have some inputs here and we have some outputs here. If we draw arrows, then say this input is mapped onto this output, this one is mapped onto this one, this one is mapped onto this one. In this particular case, our codomain contains 4 elements. This particular element here is not one of our outputs. It's not part of the range, so therefore this one here is not surjective. Okay, so that's it really. I mean, if you can do a horizontal line test as well with this one. So for example, if we have a function that looks like this. Okay, now if our domain is real and we're mapping onto, let's say this here is, let's say -1, and this point here is, let's say 1, -1. Okay, so we're going down here on the y-axis as far as -1. Now if our codomain then is from, let's say, -1 to infinity, okay, -1 to infinity, and remember this is this kind of square bracket here means that we include the -1. This curved bracket here means that we don't include infinity. Normally you wouldn't include infinity. So in this particular case, if we take our horizontal line again, so we draw any kind of a horizontal line and we start at the beginning of our codomain here, which is -1, and we move the horizontal line up and we keep moving it up to infinity, if you like. Is every single element on the y-axis actually used in our function? And we can see that it is. Our function starts at -1, if you like, and it goes off here in both directions right up to infinity. So in this case our function would be surjective. Now the last thing that we really need to know here is what's called bijective function. Bijective function. Okay. Now a bijective function is simply a combination of both. So that's all that means. So it's both injective and surjective. So if you have a function and you can show that it's injective and you can also show that it's surjective, then you can say it's bijective. If you have a function and you can show that it's not either injective or that it's not surjective, then it's not bijective. It only has to be not one of these for it not to be bijective. And that's it. So let's have a look at some examples, just a few more examples just to emphasize what we've done up here. So let's have a look at this function here. So we're going to have a look at a function, we'll call it f, and let's say it maps real onto real here. Now we'll take a linear function first of all. Okay, so we have a line going up like this, and we want to know really, this goes off in both directions, off into infinity. So that goes way up as far as you can and way down this way as far as you can as well. So it goes off in both directions. And of course our x and y axis, they go off in both directions as well into infinity. Now, is this injective, bijective, or surjective? Well, let's have a look at it. If we use the horizontal line test, we take any horizontal line and we move it up along here. Does it only hit the blue line here, the graph, in one place at all times? And it does. Okay, so we say it's injective. So it is injective. Now, also, is it surjective? Well, surjective means that we look at the codomain here, which is OR. Look at the codomain here, which is OR. And that's the entire real number line in the y direction. And we want to know, do we use every single output? Do we use every single element in the real axis? And we do. We can see this line goes off to infinity in that direction and this direction. So it uses every single element on the y-axis. So it's also surjective. And then by definition, it is bijective as well. Okay, so it is also bijective because it's both injective and surjective. Okay, so let's have a look at another one then. So we will go put in our x and y axis, and let's say this time we draw a quadratic kind of a curve here, like this. Okay, and we'll call this f again, and it'll, let's say we'll map real onto real again. Now, in this case, we can see that it is not going to be injective, because if you take a horizontal line here and move it up along, it will cut. If you take it at any position here, it cuts the graph in two places. That means for this particular y value here, for this particular y value, you've got two x values. Two different x values will give you this particular y value. Therefore, it is not injective. So this one is not injective. Okay, what about surjectivity then? Well, we can look at the codomain again. It's the real number line on the y, in the y direction. So it's all these elements in the on the y-axis. Do we use all of these values in the y on the y-axis? And the fact is we don't. We start here roughly at 0 or just a little bit above 0, and we use all the positive values on the y-axis, but we don't use any of the negative values. So therefore, it is not surjective. And by definition, then it can't be bijective either. Okay, so that's another one. Let's have a look at. Let's see. We'll have a look at one more, I think, or maybe two more. So let's just move this up again. Now, okay, so let's have a look at a quadratic kind of a curve again. So we're going to go around like this, and this time we'll call our function f again, and we will go from real. We'll go from real, and let's say this is 1 here. So we got 1, 2, and this point here at our vertex here is, let's say, I don't know, 5, 1. Okay, so we'll say that's 5 up to here, 1, 2, 3, 4, 5 along the x-axis. So real up to what? Let's say 1 and infinity again. Okay, so let's have a look at this and see, is it injective, surjective, or bijective? Okay, so first of all, injective. It can't be injective because if we draw a horizontal line anywhere along here, it's going to hit the graph, it's going to hit the curve here in 2 different places, here and here, which means there are 2 different x values to give us the same y value, so that means it's not injective. Now, what about surjectiveness here? Surjectiveness. So we take a look at our codomain. Do we use every single value from 1 up to infinity? Well, we do. 1 starts here, and we use all of these y values the whole way up along to infinity. So it is surjective. We use all the elements in our codomain. So it is surjective. And by definition it's not bijective. It can't be bijective because it's not injective. Okay, just one last one then, and that'll be it then, I think. Let's see, we'll go from, let's say we call this 1, 2, 3, and out here we'll call this pi and pi over 2, and we'll take our graph from 3 and we'll go down to 1 at pi. Okay. Now in this particular case, our function again, let's say our function will be f, and it's going to map 0 to pi, so we're only going from 0 to pi here, and we're going to map onto OR. So let's have a look at that then. Now, first of all, injectiveness. Is it injective? Well, it is. If you draw a horizontal line in the domain here from 0 up to, or sorry, along our function here, is it will it cut the graph only in one place? So if we draw a horizontal line here, move it up along here from 1 up to 3 here, it does only cut the graph in one place at any particular time. So it is injective. So it works. Our horizontal line test shows that it is injective. Now, what about surjectiveness? So it's surjectiveness, we need to look at our codomain, which is OR. Do we use the entire y-axis as our outputs? No, we don't. We don't use any values below 1, or we don't use any values above 3. So it is not surjective. Oops, it's not surjective. So it is not surjective. And again, by definition, it can't be bijective because it's not surjective. It has to be both injective and surjective to be bijective. Okay, and that's it on these type of functions.